zeros or x-intercepts of the function y equals 3x squared minus 2x minus 7. All right, on this one, what we're going to do, since it's a calculator problem, we can just go ahead and graph the function on our calculator, and when you do so, you will get something that looks like this. All right, and we are looking for the zero, so we're looking for where this graph touches the x-axis. We don't need to find the zero down here because zeros are just x-intercepts, so that's what we're going to do. And I'm going to use the zero feature on my calculator. When I do that, I'm going to get two answers. My answers are going to be negative 1.2300, and my other zero will be at 1.8970. And just make sure you go all three decimal places when you do that. Okay, number 2, find the points of intersection of the functions y equals the square root of x plus 5 and y equals 4 minus x squared. Okay, again, on this one, it is a calculator problem, so we can just go ahead and graph both functions. When I do so, I will get something that looks like that, and then I'll get something that looks like that, I do believe. So they cross 2 times. And I just need to find those points of intersection, and the feature that we will use in our calculator is the intersect feature. And if we do so, we'll have to do each of them separately, of course. The first point of intersection is going to be negative 1.455, 1.883, and my second point of intersection will be 1.227, 2.495. And again, if you're using that intersect feature, you do want to make sure that you're accurate to 3 places. Number 3, find the limit graphically. Graphically just means to draw it and figure out what's happening as we are approaching 3. So if you go ahead and graph that function, we'll have an asymptote at 3. We're going to get a picture that looks something like this. And the question asks us to find the limit as x approaches 3, so we need to find out what's happening as we're coming in from the left and what's happening as we're coming in from the right. So I'm going to find the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. So as I'm coming into 3 from the left, I'm headed down towards negative infinity, and as I'm heading towards 3 from the right side, I'm heading up towards infinity. These two limits do not meet each other, so I am going to say that this limit does not exist. And that would be because the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. Okay, problem 4, find the limit numerically. Numerically means to make a table. So I'm going to find a table as x approaches 4. So if I make my xy table, we'll have 3.9, 3.99, 3.999, and then on the other side of 4 we'll have 4.001, 4.01, and 4.1. And now what we can do is just go ahead and plug this function into our calculator, and then we will use the table feature on our calculator, and then we'll just start plugging in these values. When I do so, I'm going to get negative 0.2516, negative 0.2502, negative 0.25, negative 0.25, negative 0.2498, and negative 0.2485. So as I'm coming in from the right and as I'm coming in from the left, I definitely am approaching the same y value, which is negative 0.25, which we could also write as negative 1/4. Okay, number 5, find the limit analytically. Analytically means algebraically. Okay, so we want to, first of all, just try to plug in 3. If I plug 3 in the numerator, I'll get 0. If I plug 3 in the denominator, I'll get 0. That does not mean the limit does not exist. I just can't do it that way. So the next thing that I'm going to try to do is cancel some things out. So I'm going to have x minus 3. I'm going to factor the denominator into x plus 3 times x minus 3. My x minus 3's cancel out, so I'm left with 1 over x plus 3. I now can find the limit as x approaches 3 by plugging in 3. So when I do that, I will get 1/6, and that will be my limit. Okay, number 6. Sketch a graph of the function y equals x minus 3 over x squared minus 9. Don't forget holes and asymptotes. So we can use our calculator to graph this, but we do want to investigate it first. And we actually had a problem like this just the problem before. When I go ahead and factor this again, I'll get x minus 3 over x plus 3 times x minus 3. The x minus 3's cancel, so I'm left with 1 over x plus 3. And when I look at this, what happened, since the x minus 3 cancels out, it was a discontinuity, but it's removable, so I should see a hole at x equals 3, even though my calculator will not show that. And because at x equals negative 3, that is a non-removable discontinuity, we will see a vertical asymptote. So, and that our calculator should show that. So vertical asymptote at x equals negative 3. So when I go ahead and graph it, I should pretty much get what the picture looks like. We will see a vertical asymptote at negative 3. And the graph will go something like that. And then the other way my graph is going to be going, but at x equals 3, I need to make sure that I do put a hole in my graph. So my graph will look something like that. So we just don't want to forget that hole when we're graphing it. Number 7, find A and C so that f is differentiable on the entire line. There are two parts to this problem that we need to take into consideration. If something is differentiable, first of all, it has to be continuous in order for that to happen. So I'm going to work with continuous first. If a function is continuous, the limit from the left, which would be from the left of negative 3 this time, must equal the limit as x approaches negative 3 from the right. So that's the first thing that I'm going to tackle. So if I plug negative 3 in from the left, I'm going to get 2a times negative 3 minus 7, and that gives me negative 6a minus 7. And then from the right side, if I plug in negative 3, I'm going to get 4 times negative 3 squared minus negative 3 plus c. That's going to give me, let's see, 36 plus 3. That's going to give me 39 plus c. And in order for it to be continuous, we know that those two have to equal each other. And notice there are two variables in my problem, so at this point in time, I cannot solve for a or c. So the next thing that I'm going to be looking at is differentiable. And something being differentiable just means you can take the derivative, and it doesn't matter which one you take the derivative of, you will get the same answer. So this basically is saying that the derivative, if I plug in negative 3 from the left side, has to equal the derivative when I plug in negative 3 from the right side. So we're just going to go ahead and find both derivatives. So the derivative from the left side, the derivative of 2ax minus 7 would just be 2a. And then the derivative from the right side is going to be 8x minus 1. And remember, the c and the a are just constants. So from here, now we know there's no place to plug in x equals negative 3, so 2a just stays 2a. And on the right side, we do get to plug in negative 3. And when I do that, I'm going to get 8 times negative 3 is negative 24, minus 1 is negative 25. Okay, so from here, I actually can solve for a. So if I just divide both sides by 2, I'll get a is equal to negative 12.5, and I am halfway there. So now what I'm going to do is take a and bring it up over here. So we're going to have negative 6 times negative 12.5 minus 7 is equal to 39 plus c. So let's see, this is a non-calculator problem, so let's do the little multiplication here. 12, 15, I got 75 when I did there. 75 minus 7 equals 39 plus c. 75 minus 7 is 68 equals 39 plus c. And then we will divide or subtract 39 from both sides, and if I do that, I get 29. So c equals 29. So a equals negative 12.5, and c equals 29.